morning. Ladies and gentlemen.
Morning.
Morning. You're all feeling well. My name is Daniel Pico, and I'm here with my associates, Samuel Caluet and Christian Palomo. And for the remainder of this year, we're going to be working on a project that we have named the HAZMAT Safety and Reconnaissance Unit, or HRU for short. This is a brief overview of the presentation we're going to have in store for you this morning. We're first going to begin with a brief history about HAZMAT safety and HAZMAT response, when that all got started, as well as exploring the most recent robotics apparatus that has been applied to these sorts of scenarios, and how our device is going to differ from it. Now, getting into the problem. The problem is that at the moment, when a HAZMAT team is called on a scene, it's only when there is some very, very dangerous chemicals or dangerous concentrations of normally okay chemicals. You would see such scenarios at a chemical production plant or at a factory or anywhere where there's a processing of high concentrations of chemicals. Sometimes when they are called on the scene, they do have the luxury of knowing what chemicals they're going to be dealing with, but there are instances such as train wrecks, highway accidents involving tractor trailers which are carrying some of these chemicals, where they do not know exactly what is going to be present, except for the fact that there might be placards to warn them of such things. Apart from that, going into a hazmat scenario is very much a guessing game, and at this point I'm going to hand it over to Samuel Caluet, and he's going to explain in more detail what that entails.
Hey, Daniel. So I'm going to be talking about the benefits of our HRU unit. So the first thing it's going to do is it's going to minimize the investigation time for the situation. So it's going to be able to go in there, and the response unit will be able to see, will be communicating with the robot, going into the scene, and hopefully they can isolate the problem a lot faster. It'll be able to facilitate data gathering, and it'll relay, since it'll be relaying the communication back to the unit, they could get all that data, get the location a lot easier, hopefully, and then they could find out what the issue is and also minimize overall risk. So there will be situations that, like Daniel said, are unknowable. So this will be able to provide more of a safer, like isolation and investigation for this unit. So a little bit of a background: the HAZMAT response unit was first discovered in 1980. So what they do is, when there is a situation involving toxic or hazardous chemicals, they call this response unit, and what they do is they call the company, they communicate with the company and see what the issue is. They set up a perimeter, and they could take up to 30 minutes preparation time before entering the scene, and then they enter the scene, and due to lack of oxygen, they're only allowed in there about an hour of a time before they have to return back to be decontaminated. So how is ours different? I did a little bit of research, and I found out that there is an existing HAZMAT 3. So as you can see, the differences are that it has a 100-foot tether. It does have a manipulator arm with limited capability, and then it also has O2 sensors and other sensors built in. Ours will be non-tethered, wireless communication, and it will have climbing stairs capability, forced and non-forced entry, and it will have a sensory bed allowing for a very wide range of sensors to be implemented. So Daniel will be taking it from here, talking about forced and non-forced entry.
So, what is forced and non-forced entry? Non-forced entry is the simple act of opening a door or turning a latch, a simple procedure that us as human beings, having both arms, or even if you're an amputee and you only have one working arm, is something you take for granted until you have to actually design an apparatus that has to be able to do such things. This is a big deal because at present, most of the robotic apparatuses in existence, they can open and unlock, or not quite unlock doors, they can open doors, but there is difficulty when the door is locked, how it's going to enter into a room or enter into the building. And that brings me to the next point of forced entry. Forced entry is applying any means necessary to jimmy a door away from the frame or completely take out the lock so that now the door will behave as an unlocked door and you can gain entry. In our brief research, we discovered that the robotic apparatuses, whether it's bomb squad or SWAT team, they would have to have something else fixed to them in order to be able to perform forced entry, and for the most part, these methods are considered volatile for the environment environment that a hazmat scenario could have, which may contain chemicals that are combustible. So you don't want any fast movements, you don't want any sparks, you want stability. For our apparatus, we have selected to utilize the Jaws of Life, which is a tool that has been in development and in use since the 1960s. So it has the years of service and development, and it's a general method that fire departments as well as hazmat units in specific use when working in such hazardous environments. At this point, I'm going to hand it over to Christian Palomo. He's going to explain the sensory of the robot.
All right, thank you. First, for the sensory of the stair climbing, as stated, sometimes these hazard situations can occur in manufacturing facilities and homes. So in this case, we want to design a robot that can fully be able to investigate the entire scene. So we have stair climbing capabilities with two schools of thought, which is this tread design as well as wheel design. For our purposes, we lean towards the tread design because it is more capable all-terrain, and as well it will give us more grip when we're performing forced entry, such as Daniel had mentioned. Cameras. Camera is going to be very important for the system because it's going to be the only means of for the controller to understand what's going on in the situation. For this purpose, we're going to have many cameras for perspective, thermal camera, and as well as cameras that are going to be mounted to have visuals on the sensors that are going to be mounted to this unit. These cameras have to have streaming capabilities and as well have to be robust, that they can survive in these conditions. And here's some examples of some of the cameras we found. The sensors. Here are actually pictures of sensors that the hazmat fire team uses on a day-to-day basis. And for this, we want to not limit the user to certain applications with built-in sensors. So we're allowing to have an open sensory bed that uses clamps, such as like this foam clamp over here, to mount additional sensors depending on the situation, and to allow this robot to be more utilized in a universal scenario. As far as the controllers, we plan to use an Arduino-based system. It's an open platform. It has a lot of accessories and a lot of information and tools that we can use. We plan to use a Wi-Fi communication to communicate with the system, and as well we plan on using a system of flight controls because it's easier to learn and it has a lot of programmable buttons for our situation, and will be better utilized for all the different tasks that we need to perform. Sam's going to talk about some of the design constraints.
Thanks, Chris. Okay, so I'm going to be talking about our design constraints. So when the robot does enter the scene, it could be involved in combustible gases, so we need to make sure that this robot is contained and has a smooth profile, has sealed electrical compartments as not to create a spark and even make that situation worse. So we want to make sure that all those considerations are taken into account. We also want to make sure that we use instead of a DC brush motor, a brushless motor. So all these factors have to be taken into consideration. And then our proposed design is shown here. So we are going to use a tread system here, and then the Jaws of Life will be mounted in this type of fashion, and then we plan on implementing a sensory bed on top of the treads with a plate that will be mounted something like this, but this is our preliminary proposal design, so there's definitely going to be some adjustments. Chris is going to be talking about testing.
As I said, there's many systems on this unit, so a lot of testing needs to occur. We plan on testing in tandem with the Hialeah Fire Department and use some of the scenarios that they have to test for their firefighters, so we can gauge the effectiveness of our unit and the time and how fast it can accomplish these goals, because a lot of things are time sensitive. These are some of the survey of standards, ASME, ASTM, ISO. More importantly, we have also the OSHA. We have to abide by the OSHA standards because we are dealing with a work environment, and we have to take that into consideration. Some of our global learning components, we want to make this globally ready, not just something here in Florida for the Hialeah Fire Department. So we're going to be using the International Building Code standards to model our robot for the design so it can fit through the doorways and the hallways and go up and down the stairs that are not just here in Florida but internationally. And as well, we want to have a universal manual not just multi-language, but also visual manual with pictures for common maintenances that may need for the robot. I'm gonna leave it up to Daniel, who's gonna talk about the conclusion.
So to wrap everything up, this robotic apparatus represents a major step forward in the robotics application, specifically towards HAZMAT or first response, because it focuses on the cornerstones or the key aspects that have to be accomplished by an actual individual in there in order to perform that preliminary investigation. Thank you, ladies and gentlemen, for your time. I hope you enjoyed this presentation.
What is your budget on this unit?
Tentatively, we're looking at, if all aspects are to be accomplished, we're looking at close to $20,000.
Are you working with Hearst, IDEX, or with them?
The good news is that Hearst has willingly already donated a hydraulic jaws of life unit.
Okay.
So that aspect is actually covered.
Yeah.
It'll just be up to us to implement it and make sure it works.
On your final design proposal, where are the cameras located?
This is not quite the final design proposal, this is the tentative proposal, but some points of view that would be very important that we have been thinking about, we just haven't updated the drawing yet. Definitely there needs to be a point of view directly in line with the tool to see what the tool is grasping, and at least one other camera to monitor the driving position, and possibly a third one to perform a turret function. Separate of that, each one of the sensors, or if they are paired up, there needs to be at least one camera to read those DROs or digital readouts. Normally these handheld units, they're held by the firefighter when they're going inside of the big suit. I'm not sure if you guys have seen it, but on our overview slide, sort of an example of that. So it's kind of difficult, but all that they have to do is read the DRO and it tells them. So rather than being limited to whatever sensors we put on board, they get to basically read the DRO the same way that they would, having fastened it already to the sensor bed.
What part of the functionality is autonomous?
There's no autonomous. It's not. It's dependent on a user control. It's at some remote location away from the scene. So as far as autonomous, we don't plan on have autonomous. We may consider for stair climbing to have an autonomous function to be able to lock the robot into a position for faster stair climbing. But as far as that, no autonomous hasn't been considered.
Not even for the cameras?
And
It would not be necessary, at least not in our expectations. For the case of point of view to the tool, that should be stationary and fixed so that at all times they can see what's going on with the tool. And in the case of having the turret camera, like I mentioned, it provides the user with 360 degrees. That should cover all angles.
Could you go back to your standard slide for me, please?
Sure.
We're dealing with hazardous chemicals here. I don't see a standard that specifically addresses chemicals. So you may want to consider that as an inclusion, or have some kind of exception, if you will, one or the other. Does that make sense?
no,
It does.
yeah.
There's one little hiccup with actually having a single standard to address that. We actually
That's why I
went-
say it's with
Yes.
exceptions.
Yes, yes.
Exactly.
Well, the thing is, when we went and we actually spoke to a HAZMAT team. We asked them about what sort of standard does your guys' gear have to meet. You know what they did? They pulled out a book about this fat. It's probably about the size of a small notepad, but it's thick and it has really small print. And inside of there is just about every single type of concentrated chemical you could imagine in a factory, and what sorts of boots or suits can be used on it. It's pretty much their handbook. If we were to sit there and read this 300 or 400 page book, we would be there a while. So what we did instead is we spoke to them and we said, okay, well, in general terms, how can we address the chemical situation? And they said, well, we usually have decontamination procedures. For the most part, if the chemical is just something that needs to be diluted, that is water soluble, all it takes is a soap and water bath to neutralize any pollutant. So what we'd be looking at is picking a material that can be processed post-manufacturing so that corrosion and other reactiveness is neutralized. That makes it easy to clean. So that's how we would go about that, so that it can be dealt with similar to the suits that they actually have to put on.
Can you expand on the power requirements of this module, because it's, you know, the jaws of life, I assume they take a lot of current, and for whatever functionality it needs to be done, and where are you going to put that?
We're still considering, because they do have an electric powered jaws of life, and then they have the hydraulic power. That's obviously going to take more power usage. So we're taking that into consideration and then factoring that into the cameras. But we expect that we are going to have to use probably two 14-volt batteries or running batteries. So it just depends. We're still thinking about that. Daniel did some.
I did more research towards that. Power consumption at present, if we analyzed it considering seal lead acid, which is more easy to obtain and would definitely fit the global aspect a little better, considering that it's seal lead acid, we would be looking at some batteries that are so hefty and enormous that realistically there probably isn't enough room in the chassis for that. So we're going to have to pursue another route there to determine that. But the power consumption is high, and yes, we have been looking at it. If we can't address it, though, we really feel it's substantial.
How much does your hydraulic jaws of life weigh?
Units usually weigh between 40 and 50 pounds. The small unit that you see here, which is a completely self-contained unit, which we're favoring, this one is electronic. So assuming we were to get our hands on one of these perhaps, all that we would need to do is tap into the wiring system so we can get control of it. But all the hydraulics are internal. So this would represent a situation where less power would be needed. In the case of not using that application, we actually have to hook up hoses. It's a couple thousand PSI going into the lines, and it results in tens of thousands of spreading and cutting force.
The reason why I'm asking you is that if you put the jaws of life with that kind of weight, in that picture that you showed there, I have of your robot, I have a feeling that unless you create a counterweight at the back end, your thing is going to go like that.
That is true.
So the first thing that you need to do is to figure out how are you planning to use that and put that in there in such a way that you won't kill your robot before it even gets started.
Absolutely.
And with the smaller, the electric one, it's actually a little bit smaller than a typical jaws of life. So it weighs less. The entire unit, including the pumps inside the system, weigh approximately the same as just the jaws of life itself. And we plan to relocate certain pumps, not just use the enclosed unit the way it's built, and to redistribute the weight, because weight is a concern, especially with the stair climbing capabilities necessary for the robot.
I guess more important to that, and along the lines of what you were saying, Dr. Levy, leverage is important. Out in the field, and from what we discussed and what the HAZMAT firefighters were able to tell us, sometimes even they themselves, when using a jaws of life, it takes 2 men to grab this tool. So that's about 400 pounds. The good news and the bad news is, in our estimation of how heavy a robot of this size, in order to be able to have that tool weight, it's actually right about there. We're about 400 to 500 pounds, including batteries. So the leverage is in our favor, but absolutely we want to try to keep that moment arm close to the center. Hence the, if you notice, this right here is the pivot point for the arm. So while most robotic approaches tend to have the arm on a sort of turret, this tends to raise the actual pivot point of the arm. So we're trying to keep everything low to the center, giving it that leverage.
I mean, have you looked also at, if you're talking about a robot that weighs close to 400 pounds, have you looked at what the load maximums are for, let's say, if you you have a house that has wooden stairs going up to the second floor?
As a matter of fact, we actually have been doing some calculations towards that. We did it across several different inclines, ranging from 10 all the way to 70 degrees. Your interior stairs in a residential house, we found, is going to have between 50 to 55 degree incline, and at that amount, we did the calculation, and it would require 153 pounds of force being applied towards the treads, assuming slippage.
Yeah, but that's not what I'm asking. I'm saying that you looked at what the maximum load a stair could take before it.
By code.
Structural
That's
failure in the
where-
stairs.
That's where our code's coming from.
Yeah.
That's actually still a work in progress, and we are very worried about that, as a matter of fact. But,
On a related question, as a matter of fact, the jaws of life is going to be an impact mechanism, correct?
Negative. The jaws of life is never to be used for impact. That is what the firefighters told us. It's basically an encased hydraulic cylinder, and what they have is they have a set of shears built into the tip, and they have those spreading points on the outside. So if it was to cut something out of the way or to spread it open, you could do that, but impact, you don't want to.
Okay. Well, where I was going with my line of questioning is that if it is in fact an impact device, then you'd want to make sure it's Newton's third law compliant.
Shock absorber.
Yeah, impact or action and reaction, so that you don't get that robot kicking back. So take a good look at that and make sure.
Yes, sir.
And I just have one comment for your communication. In evaluating why previous designs may have been tethered, many of these environments that you'll be going into require special construction or special containment of these chemicals. Are you worried about shielding and loss of signal due to that?
We are considering that.